My name is Jay Alford-Lago. I'm a third-year PhD student in the Computational Science Joint Doctoral Program, and I'm going to be talking about something called scale-separated dynamic mode decomposition and how we're using it to model the ionosphere. So the ionosphere is a region of Earth's atmosphere that ranges from roughly 60 to 1,000 kilometers above Earth's surface, and it's the result of extreme ultraviolet and X-rays from the sun that produces layers of ionized atoms and molecules. As a result, there's a strong diurnal component to the ionosphere with a characteristic nighttime and daytime structure. Now, the physics of the dynamics of the ionosphere are very complex and very difficult to model because the ionosphere is coupled into a larger space weather system that includes the magnetosphere, tidal and storm forcing from the lower troposphere, composition of the neutral atmosphere, and all of this together produces this highly complex magnetohydrodynamic system that from a physics-based perspective can be very difficult to simulate numerically. Our approach then is to look at purely data-driven methods. And in this case, we're looking at something called dynamic mode decomposition, or DMD. And the idea behind DMD is that if you have a system that you wish to model, you can just start measuring the system. And you build up a time series of these snapshots of the system, which you can organize into these matrices y minus and y plus, where each column in these matrices represent a snapshot of the system at a particular time, and y plus is y minus, just each column shifted one time step into the future. And then with that, you can set up a regression problem and look for a linear operator k, this matrix k, that maps y minus to y plus. So it maps each column in y one time step into the future. And then from the eigen decomposition of K, you can generate a time stepping model from the modes and eigenvalues. For the ionosphere, the data set that we're looking at is this time series of vertical profiles of the plasma density taken from this this weather station in Boulder, Colorado. Now, if we just apply DMD to this data set naively, the model fails fairly catastrophically. And this is due to these high frequency fluctuations that we see in the data. You can see this in the Hilbert spectrum of our time series, which is a time frequency plot of the instantaneous energy in the system. And you can see that there's these high amplitude transient events interspersed throughout. And these cause large gradients in the data. And these large gradients are not conducive to that one-step linear best fit that DMD is looking for. So this motivates proper filtering techniques prior to doing anything like DMD. And the way we're doing that is by way of multi-resolution analysis via wavelet decompositions to separate scales in the data prior to doing DMD. We do these wavelet decompositions in the temporal domain, so we're separating fluctuations in the data across a number of scales. We then actually compute correlations across these scales and group highly correlated scales back together because we want to preserve coupled dynamics in the system. The result of this is we've taken our original data set and we've expanded it into this set of, in this case, 5 different time series, where each time series here corresponds to correlated scales in the data set. Now we can perform DMD on each of these individually and produce a model like we did with normal DMD. However, we're now summing over our correlated components in the data set. Here we're looking for a model of the mean plasma density profile. So there's a bit of averaging going on behind the scenes here. But the result of this SSDMD model is it produces a much better reconstruction of the data, and it still allows for future prediction of the system, forecasting of the system, by way of the modes and eigenvalues. In this case, we're using just the first 10 days of data, denoted by the vertical dotted black line here, to fit our SSDMD model. And then we're using the remaining 3 days to evaluate the forecast capability. So this research going forward will look into further improving the accuracy of such modeling techniques for space weather systems.